In this video, we'll discuss NMR chemical shift and NMR integration. Let's start with chemical shift. NMR spectra are basically plots of peak intensity on the y-axis versus chemical shift on the x-axis, measured in units called parts per million, as you can see in sample proton and carbon spectra on this slide. Chemical shift values increase from right to left. So you can see in this proton spectrum, we have 0 to the right, going all the way down to 10 or greater on the left. And in the carbon spectrum, 0 on the right, going down to 200 or greater on the left. You'll also notice that NMR peaks generally appear as sharp spikes in proton and carbon spectra. Most proton peaks are going to be absorbing between anywhere from 0 to 12 or a little bit greater parts per million. And in carbon NMR, peaks are generally between 0 and 200 or slightly greater than 200. Something else that you should keep in mind in carbon NMR is that sp3 hybridized carbons generally appear less than 100 parts per million, and sp2 hybridized carbon peaks will appear greater than 100 parts per million. And you'll notice that carbonyls, C double bond O, carbonyls will appear the furthest to the left. They'll have the highest values. We have to get used to these terms upfield and downfield. Peaks that appear to the right, that is at lower ppm value, are said to appear upfield, and peaks which appear at higher ppm values, both in proton and carbon spectra, are said to be downfield peaks. You'll frequently see peaks at 0 ppm. These have nothing to do with the compound that you're investigating, but they're an internal standard called TMS, and all chemical shifts are measured relative to TMS, and TMS by definition is set at 0 parts per million. The general rule of thumb in both proton and carbon NMR is that protons and carbons which are closest to electronegative atoms are going to appear the furthest downfield, that is the furthest to the left in the spectrum. Take a look at the examples that are shown below. For chloroethane, the hydrogens on the carbon attached to chlorine are going to be furthest downfield in the proton NMR than the hydrogens of the methyl. And in carbon NMR, the carbon attached to the chlorine is going to be further downfield than the methyl carbon. In the second example, we have a halogen on each atom, but fluorine is more electronegative than bromine, which would mean that the hydrogens and this carbon would appear furthest downfield in NMR than the hydrogens and carbon attached to bromine. In the example at the very bottom, we have 3 halogens attached to the molecule, all the same, but we have 2 halogens on this carbon and only 1 halogen on this carbon. So you would expect this carbon attached to 2 chlorines and this hydrogen attached to the carbon attached to the 2 chlorines to be furthest downfield in the proton and carbon NMR, further downfield than these hydrogens labeled HA and the carbon attached to the only 1 chlorine. These carbon spectra of molecules that contain both sp2 and sp3 hybridized carbons illustrate nicely the fact that sp2 hybridized carbons generally appear greater than 100 parts per million. As you can see, we have 1 octene. These 2 alkene carbons are greater than 100 parts per million, and we have ethylbenzene, where the benzene carbons appear greater than 100 parts per million, and notice that all of the sp3 hybridized carbons in both of these molecules appear much less than 100 parts per million. Something else that you should notice is that the sp3 hybridized carbons, which are closest to the double bond or closest to the ring that is directly attached to the sp2 hybridized carbons, appear the furthest downfield. That's because sp2 hybridized carbons are slightly more electronegative than sp3 hybridized carbons. Hydrogens directly attached to carbons that make up part of a pi system have unique chemical shift values, as you can see in this table. The one that you'll see most frequently, and the one that you really have to keep in mind most often, are hydrogens attached to benzene rings. They appear exclusively between 6.5 to about 8 parts per million. It's very common, so therefore if you see a proton spectrum that has peaks in that region, and particularly if you know that molecule has at least 4 degrees of unsaturation, remember that benzene has a ring and 3 double bonds, that's 4 degrees of unsaturation, then you should expect that that molecule has a benzene ring. When interpreting proton and carbon NMR spectra, it's extremely important to have a general idea of the chemical shifts of different types of hydrogens and carbons. For proton NMR, invariably the furthest downfield type of hydrogen would be carboxylic acids. They appear 10, 11, 12, 13 parts per million. Aldehydes are the next furthest upfield, and they're maybe between 9 and 10 parts per million. Aromatic rings invariably will be between roughly 6.5 to 8 parts per million. So if you have any peaks in a proton NMR spectrum that you are analyzing that appear in this region, you should have a clue that a benzene ring is probably present in the molecule. Here we have hydrogens attached to double bonds, which appear a little bit further upfield than those on a benzene ring. Hydrogens on carbons bearing electronegative atoms are going to be anywhere from 2.5 to 4.5. The more electronegative the atom, the further downfield this is going to be. So oxygen and halogen are more electronegative than nitrogen. So the hydrogen on a carbon bearing oxygen or halogen are going to be 3, 3.5, 4, 4.5, whereas the hydrogen on a carbon bearing nitrogen is going to be a little bit closer to 2.5. And here we have an example of a hydrogen on a carbon which is then attached to a carbon bearing electronegative atoms. As you would expect, that would be a little bit further upfield. And then all of this, just typical hydrocarbon, ethyl, methyl, propyl hydrogens are going to be way upfield, closer to about 1 part per million. In carbon NMR, the general rule of thumb is sp3 hybridized carbons appear less than 100 parts per million, and sp2 hybridized carbons appear greater than 100 parts per million. The furthest downfield peaks are always going to be those for a carbonyl. Aldehydes and ketones are the furthest downfield, 190, 200, or even greater. Those which belong to the carboxylic acid derivatives, where X is an oxygen or a nitrogen or a halogen, are going to be still downfield, but not as far downfield as aldehydes and ketones, 160 to 180 or so. Aromatic rings and carbon-carbon double bonds, as you would expect, are going to be greater than 100 parts per million. Here we see carbons which are sp3 hybridized, attached to electronegative atoms, as you would expect. They're still less than 100 parts per million, but they're further downfield than those carbons which are not attached to electronegative atoms. Let's use what we know about chemical shift to solve the following problems. How many peaks would you expect in the proton NMR spectrum of this compound? Well, there are only 2 types of hydrogens here. We have 2 methyls. One methyl is attached to oxygen, and the other one is attached to the carbonyl. So you would expect to have 2 peaks in the proton NMR spectrum. How many peaks in the carbon spectrum? Well, we have the 2 carbons for the methyls, which are non-equivalent, and we also have the carbonyl, which is also a unique type of carbon. So you would expect to have 3 peaks in the carbon NMR spectrum. Without predicting the actual ppm values for each of the peaks in the proton spectrum, how would you use chemical shift differences to distinguish between those 2 peaks? Well, we already said there were 2 types of hydrogens, and therefore 2 peaks in the proton NMR. And the way we distinguish them is that we have hydrogens on a carbon attached to oxygen, and we have hydrogens on a carbon attached to the carbonyl. The hydrogens on the carbon attached to oxygen you would expect to be further downfield than these hydrogens. So that's how you're going to be distinguishing between those two peaks. You can actually identify those two peaks based on your knowledge of chemical shift. All right, without predicting actual ppm values for each peak in the carbon spectrum, how would you use carbon chemical shift differences to distinguish between them? Well, we have three types of carbon, three peaks in the carbon spectrum. We know that the furthest downfield peak is always going to be the carbonyl. And if we use that general rule of thumb that electronegative atoms will bring peaks furthest to the left, further downfield in both proton and carbon NMR, you would expect that the methyl attached to oxygen would be further downfield than the methyl attached to the carbonyl. All right, now let's actually see if we can predict roughly what chemical shifts we would expect for the protons and carbons in this molecule using the charts on the previous 2 pages. Let's start with proton NMR. Well, we know that this is going to be further downfield, these methyl hydrogens, than this. Hydrogens on carbons attached to electronegative atoms could be anywhere from, say, 2.5 to about 4.5 parts per million. For the hydrogens on the carbon attached to a carbon, which is then attached to electronegative atoms, 1.5 to 2.5 parts per million. This is the actual proton spectrum for this molecule, and you can see that the rough estimates for chemical shifts are followed. This methyl appears at about 3.6 parts per million, and this methyl appears at about 2 parts per million. What about carbon shifts? What would you expect for the carbon shifts? Well, carbonyls are going to be the furthest downfield. We already said that aldehydes and ketones could be 190, 200, or greater, and that carboxylic acid derivatives, like this ester, would be anywhere from 160 to about 180 parts per million. For the carbon that's directly attached to oxygen, anywhere from, say, 50 to 70, and then the other carbon is going to be much further upfield, maybe 20 to 30 parts per million. Let's now focus on integration in proton NMR. The area under proton NMR peaks is proportional to the number of hydrogens which give rise to that peak. NMR spectrometers will do this calculation for you, and in older instruments what they would do is print out a little stair step above each peak, and what you would do then is measure with a ruler in whatever units that you like the length from change in slope to change in slope in each of these stair steps, and if you compared the lengths, you would then end up with the ratio of hydrogens which give rise to that peak. So in this case here, 20 to 60 is a 1 to 3 ratio. And in modern instruments, the stair step is usually omitted, and the number will appear only. Your textbook does have a few problems with the stair steps, which is why I'm showing you this. But normally you're going to be given problems where the numbers are going to be either written directly above the peak or written underneath the peaks, the integral values. Something that you have to keep in mind is that this ratio is a general ratio, a 1 to 3 ratio of hydrogens. The actual molecule that give rise to this spectrum has 12 hydrogens. 3 plus 1 does not equal 12. So this peak was not caused by 1 hydrogen, but by 3 hydrogens. And this peak was not caused by 3 hydrogens, but by 9. So the actual ratio is 9 to 3. So keep that in mind as you're interpreting NMR spectra and considering integral values. All right, use your knowledge of chemical shift and integration in order to solve this problem. We have 2 molecules, 1 and 2. They're isomers of each other. They only differ in the position of the oxygen, labeled in red. First, predict the number of signals in the proton NMR spectrum of each isomer. Well, each one has a T-butyl group and each one has a methyl group. The hydrogens on the methyls of T-butyl are all going to be equivalent, and the 3 hydrogens on the methyl will be equivalent to each other. We have 2 sets in each, so therefore we would expect 2 proton NMR signals for compounds 1 and 2. How about the ratio of areas of the signals in each spectrum, so basically the integral values? Well, in each one you have a T-butyl and a methyl. T-butyl has 9 hydrogens, methyl has 3, so you would have a 9:3 or 3:1 ratio. Below we actually have spectra of the isomers. How would you distinguish between these isomers on the basis of chemical shift and peak integration? Well, we can identify which peak belongs to the T-butyl group and which belongs to the methyl simply by the integral values. We know that there are 9 equivalent hydrogens for T-butyl and there are 3 equivalent hydrogens for methyl. So obviously this peak belongs to a T-butyl, this belongs to a methyl, this is a T-butyl peak, this is a methyl peak. You can use chemical shift information in order to actually identify which spectrum belongs to which isomer. Easiest way to do that is to look at the difference in the chemical shift values for the 2 peaks in each spectrum. For the T-butyls, they're roughly at the same chemical shift value. This is about 1.2, this is maybe about 1.4, not too much of a difference, but there's a very big difference in the chemical shift values of the methyls. This one is at less than 2 and this one is at greater than 3.5, so that's a very big difference. Again, you know that electronegative atoms are going to bring both proton and carbon shifts further to the left, further downfield, so the spectrum to the left must be the one that has the oxygen attached between the carbonyl and the T-butyl. This methyl is further away from the oxygen than it is in this example over here, this isomer. So this methyl would be the methyl at about 3.6 parts per million.